Hello and welcome. This is AQA GCSE Chemistry. This unit is called Chemical Changes. There are timestamps in the description below. Like and subscribe if you can. Other than that, let's get going. First, we're going to take a look at the reactivity of metals. Metal oxides. Many metals react with oxygen to make metal oxides. These are called oxidation reactions. For example, magnesium plus oxygen gives magnesium oxide. Metal oxides can lose oxygen to become the metal. These are called reduction reactions. Iron oxide plus carbon gives us iron plus carbon dioxide. The reactivity series. When metals react, they make positive ions. Reactive metals form positive ions more easily than less reactive metals. For example, K, which is potassium, will form potassium ions. Do this by losing an electron. An electron is lost easily by potassium atoms. Lithium will lose an electron, but it will lose it less easily. This means potassium is more reactive than lithium. The reaction of metals. In water, lithium, this will fizz, or it fizzes and bubbles. This is because hydrogen gas is produced, and it floats and moves around the surface of the water. Na, which is sodium, this fizzes and bubbles around more vigorously. It floats and moves around a bit more, and it makes a ball shape as it moves around the surface. Potassium, which has the symbol K, this fizzes vigorously and ignites to produce a lilac flame. It floats and moves around just like the others, but probably a bit more. If you're lucky, you might have seen your teacher demonstrate this. For magnesium, this has no reaction in water, but it does fizz in dilute acid. The fizzing is making hydrogen gas. The metals can be put in a reactivity series based on reactions with water and dilute acids. So these are the metals in order of reactivity. The most reactive is at the top, the least reactive is at the bottom, and you'll notice there are actually a couple of non-metals, carbon and hydrogen. They're often included because we can use those to compare reactivities. These metals here, they can be extracted from their compounds using carbon. These metals which are above carbon cannot be extracted from their compounds using carbon. That's because they are more reactive than carbon. They are too reactive. Extraction of metals. Unreactive metals such as gold are found in the earth as the metal itself. There's no reaction or chemical reaction needed to extract the metal. Most metals are found as compounds in rocks called ores. Chemical reactions are needed to extract the metal. Metals less reactive than carbon can be extracted using carbon. This is done by reduction reactions, which involves the loss of oxygen. So going back to a previous equation, we could see iron oxide was reacted with carbon to produce iron. The iron oxide was reduced. In other words, the oxygen was removed from the iron oxide. Displacement reactions. A more reactive metal displaces a less reactive metal from its compound. Here's an example. Zinc metal is placed in copper chloride solution. So here's our copper chloride solution. It has a kind of green color, and you can see the zinc metal inside the solution. Zinc is more reactive than copper, so it displaces copper from its compound. You can see from the reactivity series, zinc is higher up than copper, therefore it's more reactive. Copper comes out of the solution and appears, and the solution becomes paler. So zinc and copper chloride is a green color as we said. The zinc will displace the copper, and therefore the copper appears on the surface of the zinc. The solution becomes a little bit less green as well, a lot paler than it was before. And we can see there in the diagram, the copper has formed on the surface of the zinc. So we can summarize this in an equation, a word equation here. Zinc plus copper chloride gives us zinc chloride plus copper. How about this one? Maybe try this one for yourself. Magnesium plus iron sulfate gives us magnesium sulfate plus iron. We've got another one here, aluminium plus silver nitrate gives us aluminium nitrate and silver. And this one here, copper plus magnesium nitrate. Well, the magnesium is more reactive than the copper, so we actually have no reaction. Next, we take a look at oxidation and reduction in terms of electrons. Oxidation is the loss of electrons, and reduction is the gain of electrons. I'm sure you've seen this before, oil rig. This means oxidation is loss and reduction is gain of electrons. Ionic equations. Zinc plus copper chloride gives us zinc chloride plus copper. Here is the formula equation for that reaction. We have included the state symbols, so S is solid and AQ is aqueous, meaning dissolved in water. And we can see that the zinc in solid form is in the form of atoms in this reaction. The copper, however, is in the form of ions in its aqueous state, and the chloride is in the form of ions as well. The zinc is in the form of ions, the chloride again is in the form of ions, and the copper at the end there is in the form of atoms. We can use this to help us write an ionic equation. So we can see that the zinc changes in this reaction, so that makes it interesting for us. We can see that the copper ions change in this reaction. However, the chloride ions, the Cl-, they're called spectator ions. They don't actually change in the chemical reaction, so we remove them from the equation. This gives us the ionic equation. Ionic equations only show the particles that react in the reaction. So therefore, the ionic equation is zinc plus copper ions gives us zinc ions plus copper. We could add the state symbols here. However, in mark schemes, they tend to ignore the state symbols, so you don't need to put those in. We can see that the zinc goes from zinc atoms to zinc ions. We can represent this with a half equation. Zinc atoms lose 2 electrons, so we are left with zinc ions and 2 electrons. We can represent this with our half equation, zinc, arrow, zinc ions, and our 2 electrons. Zinc is oxidized. Remember, oxidation is loss of electrons. Copper changes from copper ions to copper atoms. Copper ions gain 2 electrons to give copper atoms. We can summarize that with our half equation like this. Copper ions plus 2 electrons gives us copper atoms. We say the copper ions are reduced. They have gained electrons. These are half equations and show which species, which means ion or atom, is reduced and which is oxidized. Let's take a look at an example. Magnesium plus iron sulfate gives us magnesium sulfate plus iron. The chemical equation is this. These are the ions that are involved. And as we did before, this shows the atoms or ions that are present in this reaction. We don't actually need to do this line for exam questions, but it might be helpful to show working like this just to help you get to the ionic equation. So we can see how the ions or atoms are in this reaction. However, we've got spectator ions again, the sulfate. These do not change, so we can remove them. This gives us the ionic equation, which is Mg plus Fe2 plus, arrow, Mg2 plus, plus Fe. The half equations are as follows. This is oxidation. Magnesium becomes magnesium ions plus 2 electrons. Magnesium has lost electrons, and as we know, oxidation is loss of electrons. And the reduction is the iron ions. Fe2 plus, add 2 electrons, gives us Fe. Example number 2. See if you can jump from the equation directly to the ionic equation. So the chemical equation is this. These are the ions that are involved. See if you can give that a go, and we'll go through it in a moment. So the ionic equation is Fe plus Cu2 plus gives us Fe2 plus Cu. And the half equations are iron is oxidized with the half equation as shown there, and the copper is reduced, or copper ions are reduced as shown by the half equation there. So you should be familiar with this for the higher tier. Let's take a look at the reactions of acids. Reactions of acids with metals. Acids can react with some metals to make a salt and hydrogen. We can summarize that in a general equation. Metal plus acid gives salt plus hydrogen. Let's take a look at an example. Here we have some magnesium metal in some hydrochloric acid, and this will react and form a salt and hydrogen gas as shown by the bubbles there. This will end up giving us our salt, which is magnesium chloride, and our hydrogen gas, which is given off. Predicting which salts are produced. A good thing to remember, which is going to help us with this, is that hydrochloric acid will produce a chloride salt, sulfuric acid will produce a sulfate salt, and nitric acid will produce a nitrate salt. So let's take a look at this one here. Magnesium plus hydrochloric acid. Well, we've got hydrochloric acid, so we're going to get a chloride salt. That actually gives us magnesium chloride plus hydrogen. The chemical equation for that is shown here. This is not balanced. Maybe you want to spend a moment, pause here and see if you can balance it. But if not, we just put a 2 in front of the hydrochloric acid. This is now balanced. Zinc with sulfuric acid. Give this one a go if you can. For this one, we have zinc sulfate plus hydrogen, and here is the balanced formula equation for that reaction. And finally, we have iron with dilute nitric acid. Iron plus nitric acid gives us iron nitrate plus hydrogen. And again, here is the balanced formula equation. For the higher tier, we need to be able to talk about redox reactions when we have reactions of acid with metals. So let's take a look at the reaction of zinc with sulfuric acid. You might be a little bit ahead here and already know the products. However, let's take a look at the redox reactions. So here's our zinc reacting in our sulfuric acid, and here's our balanced formula equation along with the state symbols. Remember, S is solid and AQ is aqueous, meaning dissolved in water. So the ions, atoms or molecules that are present here are zinc atoms, hydrogen ions, sulfate ions, zinc ions, sulfate ions again, and hydrogen molecules. The sulfate ions are spectator ions because they don't change in the reaction, so we can take those out. And therefore we have our ionic equation, which is zinc plus 2H plus, arrow Zn2 plus plus H2. So we could take a look at our ionic equation. We've got Zn plus 2H plus gives us Zn2 plus plus H2. Half equations. The zinc changes from atoms to ions. So we can say that zinc becomes zinc ions plus 2 electrons. This is oxidation because zinc has lost electrons. Remember from oil rig. And then the hydrogen, this is what happens there. We've got hydrogen ions becoming hydrogen molecules. So 2H plus 2 electrons gives us H2, which is hydrogen gas. We refer to these as redox reactions because reduction and oxygen happens at the same time. Let's take a look at another example, reaction of magnesium with hydrochloric acid. Here's the balanced formula equation. Pause here if you want to give this one a go. If not, we have our ions in this reaction. We can see that the chloride ions are spectator ions, so we can remove those. This is our ionic equation. And our half equations are as follows. Magnesium becomes magnesium ions, so Mg, arrow Mg2 plus 2 electrons. This is oxidation. And hydrogen ions become hydrogen molecules. So again, similar to before, there is our half equation for hydrogen ions. This is reduction. And then we could try one final one. Pause here, give this one a go. So here are the atoms, ions, or molecules. This is just here to help us with our working. You don't actually often get a mark for doing this part. The mark is usually available for writing the ionic equation, but the line above helps us get to the ionic equation. So there's our ionic equation. Hopefully you're getting the hang of it by now. Here's our half equations. Iron becomes iron ions. So there's our oxidation reaction there. and hydrogen ions become hydrogen molecules. So here's our half equation for that reaction. And this is reduction. Do go over the last couple of slides again if you need to, because a lot of it is for the higher tier. But for now, let's move on to neutralization of acids and salt production. When acid reacts with a base or alkali, a salt and water are produced. Alkalis neutralize acids. So here is an acid, here is an alkali, and here is our neutral solution. Acid plus alkali gives salt and water. This is something you need to know and remember. An alkali is a soluble metal hydroxide, for example, sodium hydroxide. Bases neutralize acids. Here's our acid again, here's a base, and here's our neutral solution. Acid plus base gives salt and water. If you can remember the first one, number one, this is quite easy to remember as well. Just replace alkali with base. Bases are insoluble metal hydroxides and all metal oxides. For example, copper hydroxide or copper oxide. Metal carbonates neutralize acids. Here's our acid, here's a metal carbonate, and here's our neutral solution. Acid plus metal carbonate gives us salt and water, similar to above. However, if we have a metal carbonate, we also get the production of carbon dioxide gas, as shown by the bubbles in the conical flask above. An example of a metal carbonate is magnesium carbonate. Again, remember the salts that are produced. Hydrochloric acid produces chloride salts, sulfuric acid produces sulfate salts, and nitric acid produces nitrate salts. Here are a few that you can try for yourself to find out or predict what the products are for each of these. So we'll give it a little pause here, give it a go. And here are the answers. For the first one, sodium chloride and water, copper sulfate and water, calcium nitrate plus water plus carbon dioxide, zinc sulfate plus water, magnesium nitrate plus water, and finally magnesium nitrate with water. Hopefully that was not too tricky. Next, let's take a look at soluble salts. A soluble salt can be made by reacting an insoluble substance, for example a metal oxide, metal hydroxide, or a metal carbonate. And we can react any one of these with an acid, for example sulfuric acid or hydrochloric acid or nitric acid. A summary of the process to make a soluble salt. We react until the solid is in excess in the acid. We filter the excess solid that has not reacted, and then we crystallize the salt solution that has been produced. This is a required practical, so we can go through the steps for doing that, making a pure, dry sample of a soluble salt. We are going to make copper sulfate using copper oxide and sulfuric acid. If you react those two together, we get copper sulfate and water. You should be able to choose the right acid and the right insoluble solid depending on the salt that we're trying to make. First step, we have our dilute sulfuric acid. We gently warm the sulfuric acid in a beaker, being careful not to boil it. We then add our copper oxide. So we add some copper oxide and stir. And when we stir, we see the appearance of a blue solution. That's our copper sulfate solution. We keep adding copper oxide until no more reacts. This will be shown by excess unreacted solid at the bottom of the beaker. We would then filter to remove any excess copper oxide. Then we would use an evaporating basin and we would place our filtered copper sulfate into our evaporating basin, and we would use a water bath to gently warm our copper sulfate solution. We would heat gently using a water bath or an electric heater until you start to see the solid appear around the edges. Once we see that, we would leave the solution to crystallize, usually for a day or two, and then we would pat the crystals dry with filter paper if needed. Here is an example of some crystals made by this method You may have done this at school, and I'm sure you would have got some slightly larger crystals than I got there, but that's how you do it. The pH scale and neutralization. Acidity or alkalinity can be measured with, that should say measured, there we go. Acidity or alkalinity can be measured with universal indicator. That's not the only kind of indicator, but the common one we use is universal. So here we have two solutions. Here's our universal indicator. We can see the first one is acid and the second one is alkali. We would then use a pH scale to determine the pH of our solution. So we can see the first one on the left hand side that has a pH of 3, that's our acid, and the other one has a pH of 13, that's our alkali. We can also use a pH probe that will give us a more accurate value of pH. If we have a pH of less than 7, we will have an acid. A pH of higher than 7 will be an alkali, and a pH of 7 we describe as neutral. It's neither acid nor alkali. Neutralization equation. In neutralization reactions, hydrogen ions react with hydroxide ions to form water. Acids are solutions that contain hydrogen ions. So here's an acid, and this is hydrochloric acid, and the hydrochloric acid will break up into ions, hydrogen ions and chloride ions, and it's the hydrogen ions there that make this solution acidic or make it an acid. Alkalis are solutions that contain hydroxide ions. So here's our alkali solution. This is sodium hydroxide as an example. We have sodium ions and hydroxide ions in there, and it's the hydroxide ions that make this solution an alkali. In neutralization reactions, hydrogen ions react with hydroxide ions to form water. So there's our hydrogen and hydroxide ions. They react together with the formation of water. The neutralization reaction can be summarized like this. This has been asked a couple of times on past papers that I've looked at, so probably quite important to make a note of and remember that. Let's take a look at strong and weak acids. 3 examples of strong acids include hydrochloric, sulfuric, and nitric. Examples of weak acids, we have ethanoic acid, found in vinegar, citric acid, found in fruits, and carbonic acid, found in fizzy drinks. The pH of an acid depends on the concentration of hydrogen ions present. So let's compare strong acids to weak acids. So here's a strong acid, here's a weak acid, and our strong acid example there we have is hydrochloric acid, HCl, and as we know, this dissociates or breaks down into hydrogen ions and chloride ions, and it's the hydrogen ions that make the acid. And for ethanoic acid, which is an example of a weak acid, this is broken down like so, again producing hydrogen ions. However, why is one weak and one strong? Well, for our hydrochloric acid, we could see that it breaks down into hydrogen ions and chloride ions. But for our ethanoic acid, we can see that it does break down into 2 sets of ions, including hydrogen ions. However, for the hydrochloric acid, we have full ionization. And for our ethanoic acid, our weak acid, we have partial ionization. The ionization is reversible. That's why it's only partial. We know it's reversible because of this sign here. So this is why ethanoic and the other weak acids are weak. So let's show a final and important point. For a strong acid and a weak acid, we can have the exact same concentration. So for our strong acid, it's 0.01 moles per decimeter cubed. And for our weak acid, it's also 0.01 moles per decimeter cubed. However, the pH for our strong acid is pH 2. That means it's more acidic. And our pH for our weak acid is 4. So the hydrochloric is more acidic and the ethanoic is less acidic. For the same concentration, the strong acid has a lower pH, it's more acidic. And this is the key and important point. Strong acids fully ionize, weak acids partially ionize. Acids and hydrogen ion concentration. Here we have some pH values for some acids. Weak acid is pH 6 and the strongest acid is pH 0. And very important to remember that for every drop in a pH of 1, the hydrogen ion concentration increases times 10. So if we're looking at the hydrogen ion concentrations, if we go from pH 6 to pH 5, the hydrogen ion concentration becomes 10 times bigger. So for every drop in pH of 1, the hydrogen ion concentration becomes 10 times greater. If we had a pH drop of 2, it would be times 10 times 10, which would be times 100 times more concentrated for a pH drop of 2. Let's have a little bit of a practice. If we've got a change in pH from 5 to 3, what change do we have in hydrogen ion concentration? Well, that's a pH drop of 2, so it's 100 times higher. The concentration of hydrogen ions is 100 times higher. If we go from 5 to 1, have a think. This is a 10,000 times higher concentration of hydrogen ions. What if we don't decrease pH? What if we increase pH from 4 to 6? In this case, we get 100 times lower concentration of hydrogen ions. Let's take a look at an exam type question. We have some hydrochloric acid, the pH is 4.5, and the concentration of hydrogen ions is 3.16 times 10 to the minus 5 moles per decimeter cubed. What is the concentration of hydrogen ions in a solution of hydrochloric acid with a pH of 2.5? Well, the drop in pH is 2, so there's an increase in concentration of times 100. So we do 3.16 times 10 to the minus 5 times 100, which gives us 3.16 times 10 to the minus 3. That would be worth a mark to do that calculation in an exam. Next, let's take a look at electrolysis. Electrolysis. This is using electricity to break down compounds into elements. The compounds that we're talking about are usually ionic, and the compound must be melted or dissolved before we can do electrolysis on it. This allows the ions to move freely. The liquid or the solution is known as the electrolyte, and here is some electrolysis apparatus. Here's a cell, here's a lamp, here's the anode, which is our positive electrode, and here's the cathode, which is our negative electrode. The electrolyte is shown here, and when a current flows, positive ions move to the negative electrode, and negative ions that will be in the liquid or solution move to the positive electrode. This is because opposite charges attract. Once melted or dissolved, the liquid or solution can conduct electricity. I've put the lamp in that circuit just to show that it can conduct electricity, so the lamp would light up. Of course, there's a slight error there. The switch is not closed, so we would have to have the switch closed for that lamp to light up and for electrolysis to work. Let's have a look at the electrolysis of lead bromide. This is PbBr2. We take our lead bromide, we would heat it to melt it, and melting it will cause the ions to separate. This is important so they are free to move, or they are able to move freely. We would have bromide ions and lead ions as shown there. Here's our apparatus as before, but this time we have bromide ions in our liquid and we have lead ions as shown there. So let's see what happens. Bromide ions are attracted to the anode because the anode is positive and opposite charges attract. When they get there, they are discharged, and bromine gas is formed. For our lead ions, they are attracted to the cathode because opposite charges attract, and they are discharged as well. Lead metal is formed. For the higher tier, we need to be able to write half equations for electrolysis. So, remember, negative ions have extra electrons. This is from our previous videos on atomic structure, so you may want to go back and take a look at that if you're not sure. But negative ions have extra electrons, and negative ions can become atoms by losing electrons. Positive ions are missing electrons compared to the atom. Positive ions can become atoms by gaining electrons. So we can look at this simply by looking at our anode and our cathode. And here are our bromide ions in our liquid. They are attracted to the anode, as we said, and when they get there, they are discharged. In other words, they lose the electrons to become bromide ions, which combine together to make bromine molecules, and this is given off as bromine gas. We can write that as a half equation. Bromide ions, two of them, will form a bromine molecule and 2 electrons. For our cathode, we have our lead ions. These are attracted to the cathode, and these combine with the electrons to form lead atoms. We can summarize that with the half equation like this. Lead ions, which have a charge of 2+, will gain 2 electrons to become lead atoms. Try this one for yourself. We've got the electrolysis of molten or melted zinc chloride. Zinc ions have a charge of 2+, and they will form zinc metal, and chloride ions have a charge of Cl-, and they will form chlorine gas. So pause here, give it a go, see if you can work out the half equations. So at the anode, we have 2 Cl-, which gives Cl2 plus 2E-. You might ask yourself, why is it Cl2? It's because chlorine is a halogen, and all of the halogens exist as pairs of atoms joined to make a molecule. So that's why it's Cl2. At the cathode, we have zinc with a charge of 2+, which gains 2 electrons to form zinc atoms. Using electrolysis to extract metals. Let's remind ourselves of part of the reactivity series. We can see that metals above carbon in the reactivity series cannot be extracted using carbon, and metals below carbon can be extracted using carbon. If a metal is more reactive than carbon, then it cannot be extracted using carbon. Electrolysis is used if the metal is too reactive to be extracted by reduction with carbon. Electrolysis of metal compounds requires a large amount of energy and electrical current. One example is the electrolysis of aluminium oxide to produce aluminium. Electrolysis of aluminium oxide. Here is the apparatus that we use, that's shown in 3D. So it's a big tank with the design shown here. However, if we were to slice this in half, we could produce a 2D diagram of that, which would look a bit like this. Here we have our molten aluminium that's produced. Here we have our melted aluminium oxide mixed with something called cryolite. And cryolite is mixed in with the aluminium oxide because it reduces the melting point of aluminium oxide. This means less energy is required to melt the aluminium oxide. Here are our ions in our electrolyte. Here we have our carbon anode and our carbon cathode as shown in the diagram there. At the cathode, we have aluminium ions which gain 3 electrons to become aluminium atoms and then aluminium metal. At the anode, we have oxide ions which produce oxygen gas as shown by the half equation there. Oxygen gas is produced at the anode. The carbon anode has to be replaced regularly because it decomposes when reacting with the oxygen that's produced there. We have carbon plus oxygen, which produces carbon dioxide gas. Carbon in the form of graphite is used for the electrodes because it's a good conductor of electricity and it has a high melting point, so it won't melt in the apparatus. The formation of carbon dioxide, however, at the anode contributes to carbon dioxide in the atmosphere and contributes to the greenhouse effect. Next, the electrolysis of aqueous solutions. Aqueous solutions are made when a substance dissolves in water. For example, sodium chloride solution, NaCl, with the aqueous there to show it's dissolved in water. Here's our sodium chloride solution. Add some sodium chloride, common salt, give it a mix or a stir, should we say. And if we were to look in the solution, we would notice that there are, in fact, several different types of ion. Those ions are sodium ions and chloride ions, as you'd expect, but because it's in solution, we also have hydrogen ions and hydroxide ions which come from the water. So those are the ions that will be present in that solution. So we have two positive ions, sodium ions and hydrogen ions, and we have two sets of negative ions, chloride ions and hydroxide ions. If we were to carry out electrolysis, the anode would attract the hydroxide ions and the chloride ions, and the cathode would attract the sodium ions and the hydrogen ions. Only one of the ions will interact with the electrode and produce the substance. Which one is it? Well, we can work it out in the following way. At the anode and the cathode, we have rules to help us remember. So in our solution, we will have hydroxide, hydrogen, chloride, and sodium ions, and they are attracted, as we can see here. Hydroxide and chloride to the anode, hydrogen ions and sodium ions to the cathode. The rule to remember is that if halide ions are present, the halogen will form. By halide ions, we're talking about ions formed from elements in group 7. The halogens are group 7 elements. If we don't have a halide present, oxygen gas will form. So in this example, we do have a halide ion present. That's the chloride ions from group 7. That means chlorine gas will be formed from chloride ions. And we can write the half equation as we did before. 2Cl minus gives us Cl2 plus 2E minus. And at the cathode, hydrogen is produced if the metal is more reactive than hydrogen. A simpler way to remember that might be the least reactive substance will form. That will help us predict, but if they ask you in a question, why is hydrogen produced, then you would use the idea that hydrogen is produced because the metal is more reactive than hydrogen. But an easy way to predict is to use the idea that the least reactive substance will form. Here's our reactivity series, and we can see that hydrogen gas will form because hydrogen is less reactive than our sodium ions. And here's our half equation for the production of hydrogen gas. 2H plus 2E minus gives us H2. And finally, for this unit, for the higher tier, we need to talk about half equations and include the idea of oxidation and reduction. Here are a bunch of ions that we're going to use for these examples. And remember, Euler rig will help us remember what is oxidized and what is reduced. So let's look at the electrolysis of aqueous potassium iodide. So in this case, we'll have potassium ions and iodide ions, and also hydroxide ions and hydrogen ions. At the cathode, potassium ions and hydrogen ions are attracted. However, if we look at the rule above, the least reactive out of those two is hydrogen, so hydrogen gas is going to be formed. Here's our half equation. 2H plus 2E minus gives us H2. And we know this is reduction because electrons are gained by hydrogen ions. Reduction is gain of electrons. At the anode, we have hydroxide ions and iodide ions which are attracted. The halide ion, which is iodide from group 7, is present, so iodine is going to be produced. 2I minus gives us I2 plus 2E minus. This is oxidation because electrons are lost from iodide ions. One more example, copper nitrate solution. We have copper ions, nitrate ions, hydroxide ions, and hydrogen ions. So maybe pause here, give this one a go. At the cathode, we have copper ions and hydrogen ions which are attracted, but the least reactive is copper. So the half equation is Cu2 plus 2E minus gives us Cu. This is reduction because electrons are gained by copper ions. And at the anode, we have OH minus and nitrate ions which are attracted. There is no halide present there, so the oxygen is produced. Here's our half equation for oxygen. Slightly awkward, slightly more tricky to work out compared to the other ones, so it might be a good idea just to memorize that one in case it comes up in your paper. And this is oxidation because electrons are lost from hydroxide ions. So that's it, AQA GCSE Chemistry for Combined Science. Thank you for watching, and I'll catch you in the next one.